Hello and welcome. I'm really glad you're here. Maybe you've just turned down the lights. Maybe the room is still, your body softening into the bed, or maybe you've found a quiet moment in the middle of a busy day. However you've arrived, this is a space made gently for you. A calm corner of the universe where questions can unfold slowly and where curiosity doesn't need to chase answers. It just drifts, like a feather on air. Tonight we're going to explore a question that's lived on the edge of wonder for a very long time. Not something loud or urgent, just a quiet mystery that hovers at the edge of what we know. What lies beyond the observable universe? We'll follow that question slowly, not in a rush, not in a lecture, just a meander through space and time, like two people looking up at the sky and asking softly, "What's out there?" Now, if you're already enjoying this quiet moment, I'd love it if you gave the video a gentle like. Nothing too bright, just a soft signal. And if you'd like more sleepy science stories like this one, you can subscribe. They're all made with the same intention: calm, comfort, and a sense of awe that doesn't demand anything from you. And if you're listening from somewhere special, a forest cabin, a rooftop in the city, a small village I'll probably never see, let me know in the comments. I love watching the bedtime map gently light up, one person at a time. Just a small reminder, this video, like all others here, is for relaxation and gentle learning. It's not a substitute for medical advice or professional sleep help, just a peaceful place to let your thoughts slow down, to rest if you need to, or to drift if you want to. So now, if you're ready, you can lie back, let your shoulders soften, take a slow breath, and look up, in your mind or through the ceiling or out a window. It doesn't really matter. The night sky's always there, full of stars, full of silence, full of questions. And tonight, we'll begin with one that has no edges, only distance. What lies beyond the observable universe? When you look up at the night sky, what you see is not just space. You're looking at time. The stars above you are not where they appear to be, and they are not when they appear to be either. Some of the light reaching your eyes tonight left its source hundreds or thousands of years ago. In some cases, millions. That light has been travelling all this time across emptiness, through expanding space. And now, only now, it reaches you, quietly, casually, as if it hasn't been crossing the universe for eons. This is what we mean when we talk about the horizon of light. It's not a visible edge. You won't find a line across the sky where light stops and darkness begins. It's a concept, one that describes how far light has had time to travel since the beginning of the universe, because there hasn't been an infinite amount of time. The universe began, at least as far as we understand, around 13.8 billion years ago. That's when space and time as we know it came into being. Before that, we don't have reliable physics. We have ideas, hypotheses. But the solid, measurable part of the story begins with the Big Bang. From that moment onward, light has been spreading. At first, the universe was too hot and dense for light to travel freely. It was more like a fog than a space. Photons, the particles of light, were trapped, scattered constantly by free-floating particles. Then, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Electrons settled into place, the fog cleared, and light began to move, unimpeded. That first light is still travelling. We call it the cosmic microwave background, or CMB. It's the oldest light we can detect, not with our eyes, but with instruments. When scientists measure the CMB, they're looking at a moment just after the beginning, a time when the universe first became transparent. That light has stretched and cooled as space expanded, changing from high-energy radiation to a soft, cold glow in the microwave spectrum. It's everywhere. No matter which direction you point a sensitive enough detector, you'll find it. Faint, uniform, ancient. But even that light comes from within our horizon. Beyond that, there may be galaxies, stars, entire structures, but their light hasn't reached us. There hasn't been enough time, and because the universe is expanding, not slowly, but at an accelerating rate, many of those distant regions never will be visible. The light they send today will never get here, not because it's too faint, but because the space between us and them is growing too fast. This might seem strange, even a little uncomfortable. We're used to thinking that if we wait long enough we can see farther, like watching a ship come over the horizon of the sea. But in the case of the universe, some ships are sailing away faster than light could ever reach them. They're not even fading into the distance, they're being pulled beyond reach. That's what the horizon of light represents. It's not a boundary of space, but a limit of connection. A point beyond which events can no longer affect us, no matter how much time passes. Imagine you're standing on a frozen lake, and someone drops a pebble far off in the distance. The ripples can only travel so fast. If the ice is stretching beneath your feet faster than the ripples can move, you'll never feel them. The event happened. The pebble fell. But it's lost to you. You'll never know it happened. That's how it is with parts of the universe. They exist. But they're disconnected from us. Not because they're too far, but because the connection is being pulled apart by expansion itself. This isn't a temporary effect. It's baked into the structure of how space behaves. When we speak of the observable universe, we're referring to the region from which light has had time to reach us since the beginning. It's a sphere around us, not because we're at the centre of the universe, but because we're at the centre of our own past light cone. Every observer in the universe has their own observable universe. If there's someone right now, halfway across the cosmos, lying quietly on a planet circling a distant star, their sky looks different. Their horizon surrounds them, centred on their own place in space and time. The edges don't match ours. The stars they can see may include some we'll never witness, and vice versa. It helps to think of light not as something instantaneous, but as something that travels. We forget that because light moves so fast. On Earth, it's almost immediate. From the sun to the Earth, about 8 minutes. From the moon, a little over 1 second. But across the universe, those seconds stack up into years, and then into centuries, and then into something stranger. Deep time. The most distant galaxy we've observed is called GNZ 11. The light from that galaxy left more than 13 billion years ago. That means we're seeing it as it was when the universe was just a few 100 million years old. But because space has expanded since that light began travelling, the actual distance to GNZ 11 now is not 13 billion light years. It's more like 32 billion. And that's just one example. Many objects we see in the deep sky are much farther away now than they were when the light left them. This means the observable universe is not simply a bubble of 13.8 billion light years. It's much larger, about 46 billion light years in every direction. That gives it a total diameter of around 93 billion light years, and still, it's just the part we can see. Beyond that, we don't stop expecting things. The uniformity of the cosmic microwave background suggests that conditions were similar in all directions. No matter where we look, we see the same faint glow, with only tiny variations. That's important. It tells us that the early universe was nearly the same everywhere. Evenly distributed, well mixed, without sudden shifts or breaks. So we expect that the part of the universe we can't see continues in much the same way. We have every reason to believe the universe extends far beyond the horizon of the light. Still, there's a difference between what we expect and what we can prove. Our models, our equations, even our observations, they all rely on light reaching us. That light is our messenger. And like all messengers, it's limited by time and distance. Sometimes people ask, what if there's something completely different beyond the observable universe? Another type of physics, a different set of constants, a kind of structure we've never imagined. It's possible, but it's not testable, and for science that distinction matters. We can explore ideas, we can build simulations, but until light or some other form of measurable signal reaches us, we can't confirm anything. That's why the horizon of light is not just a distance, it's a line between knowledge and speculation. Everything within that line is subject to observation, study, and evidence. Beyond it, we have only theory and inference. The expansion of the universe makes this line more important over time. It doesn't stay fixed. It changes as the universe evolves. In the early universe, everything was closer together. Galaxies were more compact. The horizon was smaller. As time passed, more light had time to reach us, and the observable universe grew. But there's a limit. Because of accelerating expansion, there are regions that are already beyond reach. Their light will never reach us, no matter how long we wait. In the distant future, billions of years from now, the observable universe may actually contain fewer galaxies than today. Not because galaxies are disappearing, but because the space between us and them is growing so quickly that their light will never reach us again. They will fade not into darkness, but into absence. This isn't something to fear. It's just a part of how space behaves, a natural consequence of the universe's rules. We are lucky to be living in a time when the universe is still visible in all its vastness, when we can see galaxies billions of light years away, when the ancient light of the microwave background still surrounds us. In the future, that visibility will shrink. The universe won't go away, but the evidence of its past will become harder to find. That's one reason why scientists work now to map the sky so carefully, to gather light while it's still arriving, to record the signals before they slip past our horizon. Every telescope, every mission, every survey. It's part of a race, not against time, but against distance. But here's something else to think about. Even if we can't see beyond the horizon of the light, we can feel confident that space continues. Gravity doesn't stop at the edge of observation. The laws of physics don't suddenly collapse. The patterns we see, the arrangement of galaxies, the cosmic web of structure, they don't suggest a sudden end. If anything, they suggest continuity. A vast, possibly infinite canvas that stretches beyond our ability to see, but not beyond our ability to imagine. That's where we are right now, at the edge of the known. Not because we've reached the end of space, but because we've reached the end of light. And what lies beyond that, that's where we're headed next. It's a strange thing to wonder how far forever really goes. The question sounds simple, like something a child might ask while staring at the sky. But it's one of those questions that grows heavier the longer you sit with it. In a way, it's not about numbers or measurements. It's about what kind of universe we live in. Not just how much of it we can see, but how much of it there is, even if no one is there to see it at all. You've probably heard the word infinite used to describe the universe. It comes up in books, in classrooms, and conversations about space. But infinite doesn't just mean very big. It means no boundary, no edge, no ending. A place that goes on not for billions or trillions of miles, but with no end at all. And that's something the human mind isn't really built to picture. We're used to things being contained. Rooms have walls, oceans have shores, even our planet, vast as it feels, is round. You can circle it, you can measure it, you can map every part. But space doesn't work like that. The universe might be infinite, it also might not. That's still an open question in cosmology, one we haven't been able to answer with certainty. What we know is that the observable universe has a size, about 93 billion light-years across, give or take. That's just the bubble of space around us where light has had enough time to arrive since the Big Bang. Beyond that, things likely continue. The question is how far and in what shape. The shape matters more than you might think. If the universe is spatially flat, and all measurements so far suggest that it is, then it might well be infinite. A flat geometry implies that if you move in a straight line, you never loop back, you just keep going. That's different from living on the surface of a sphere, like Earth, where if you walk in one direction long enough, you eventually return to your starting point. That's what we mean by a closed universe. It has no physical edge, but it curves in on itself, finite but unbounded. On the other hand, an infinite flat universe is like an endless plane. It keeps going. There's no border to cross, no outer rim. You could fly in a straight line forever and never hit a wall. But here's where it gets even stranger. Even if the universe is infinite, we will never know for sure. Not from inside the observable bubble. No matter how long we wait, no matter how advanced our instruments become, there will always be a limit to what light can reach us. The edge of what we can see will never show us the edge of what exists, if an edge exists at all. So how far is forever? If you're asking how far space itself stretches, the honest answer is that we don't know. It might go on without limit. It might curve back on itself in a shape too large for us to detect. The data we have suggests flatness, which supports the idea of infinity. But to be rigorous, we have to admit that very large and infinite are not the same. The observable universe might be a small patch of a larger whole, and even that larger whole might still be finite. Just enormous. There's another layer to this, and it comes from inflation theory. Right after the Big Bang, space is believed to have undergone a rapid and violent expansion, faster than the speed of light. This inflationary period smoothed out irregularities, spread out matter, and set the stage for everything that followed. But one consequence of this inflation is that it might have stretched the universe so far, so fast, that the region we occupy is just a tiny section of something far bigger. Maybe even an infinite expanse. If inflation never really ended in some regions, then entire other pockets of space could exist, each with its own observable universe. We'd be one among many, and not the largest, not the oldest, just one. This leads to the idea of the cosmic patch. Imagine the universe as a giant quilt. Each patch is a region where inflation ended and a bubble of normal space began to grow. Our patch is the observable universe. Others could be out there, beyond our light horizon, unreachable and unseeable, but still real. And this brings up an uncomfortable truth. There are limits to observation. There may be truths that are real, but permanently outside the reach of evidence. Not because we don't have the tools, but because the laws of nature themselves place a boundary between what can be known and what cannot. That doesn't mean we stop asking. It means we carry the question carefully, knowing that its answer might always live at a distance. Sometimes, when people hear this, they imagine the universe like a giant room, a flat plane, going on forever, dotted with galaxies. But forever doesn't mean uniform. There are places, even in the observable universe, where galaxies are more clustered, and other places where things are more sparse. If the universe is infinite, that patchiness probably continues. There could be regions with more stars, fewer stars, strange arrangements of matter we've never seen. Maybe there are giant voids, hundreds of millions of light years across, where almost nothing exists at all. Not because something erased them, just because fluctuations in the early universe left them that way. The strange part is, in an infinite universe, not only is everything possible, everything that can happen will, somewhere. Given enough space, matter will arrange itself in every configuration allowed by physics. That includes planets, galaxies, and yes, even exact copies of you, down to your breath, your heartbeat, your thoughts. Not because the universe is trying to repeat itself, but because infinite variation guarantees repetition. It's not a certainty, but it's allowed, and in cosmology, allowed is often as far as we can go. That idea can feel overwhelming, but it doesn't have to. You're not one of many versions of yourself lost in a cosmic hall of mirrors. You're you. Your moment is yours. Even if there are infinite others, they don't take away from this one. The light you see, the stars above your head, they're part of your sky, your stretch of the universe. The rest may be unknowable, but it's not more real than what you have here. When cosmologists talk about the size of the universe, they often switch between what's observable and what's theoretical. The observable part is well measured, but beyond that, it's all inference. Theory suggests space goes on. That inflation made sure of it. But until we find a way to test those regions, which may never be possible, they remain outside science, and deep in philosophy. So how far is forever? As far as space allows, as far as time can stretch, as far as imagination reaches when observation can't. And maybe that's what makes the question so human. Not that we can answer it, but that we keep asking, we keep wondering. We keep turning our faces to the sky and measuring what can't be touched, not to control it, but just to know that we're part of something bigger. If that forever includes more galaxies, more stars, more space, we accept it. If it includes repetition, or variations of ourselves or entire regions that will never light up our sky, we accept that too. Because the point isn't to see it all, it's to understand what we can with the time we have, and to carry the rest as quiet possibility. That's where we are now, at the edge of certainty, staring into something larger than our instruments, larger than our lifetimes. And from here, we'll keep going, into how we measure these distances, what we really mean by speed and light and limits, and why the universe's expansion keeps reshaping the answers. But we don't have to rush. Let that question linger a little longer. How far is forever? Maybe far enough that we'll never see its end, and maybe close enough to feel it, right now, in the stillness between thoughts. There's something quiet and steady about the way light moves. It doesn't rush, it doesn't slow down, it just travels, always at the same pace no matter who is watching or how fast they're moving. In space, that pace defines everything we can know, not just what we see, but when we see it. Not just how far, but how real something feels. The speed of light isn't just a number, it's a rule. About 792 kilometers per second, or roughly 186,000 miles per second. In 1 second, a beam of light could circle the Earth more than 7 times. It's so fast that we don't notice the delay in everyday life. When you turn on a lamp, the light feels instant. When you look at the moon, it seems right there, but its light is already a little over a second old. The sun, 8 minutes, every time you look at it, and hopefully not directly, you're seeing it the way it was 8 minutes ago. In space, those delays become larger. A star 10 light years away is a star you see as it was 10 years ago. A galaxy 2 billion light years away shines with a light that left 2 billion years before you were born. You're not looking across space, you're looking into history. Light is not just an image, it's a record of what was. That's why the speed of light is called the speed limit of the universe. Nothing, no signal, no object, no idea, can move faster. It isn't a technical problem, it's a built-in feature of how reality behaves. And that limit defines the observable universe. Not because we've reached the edge of space, but because we've reached the limit of how fast information can travel. It's not just that we can't go faster, it's that no effect can reach us more quickly. No event, no explosion, no motion can communicate across the cosmos faster than light can move. So when we look into deep space, we're not just looking far, we're waiting, and we're only aware of the parts of the universe whose light has had enough time to reach us. You might wonder, what if we sent something faster? A spacecraft, a message, a wave? But every theory we have, from Einstein's relativity to quantum field theory, says the same thing. That limit is hard. Not because we haven't figured out how to break it, but because it doesn't break. In fact, strange things happen as you approach it. If you tried to accelerate to the speed of a light, your mass would increase, your energy needs would climb to infinity, and time would slow down from your perspective. At the limit, the rules collapse. The universe holds the line. That's why when we talk about what lies beyond the observable universe, we're really talking about a horizon set by time, and this constant speed. There could be stars just past that line, whole galaxies, but their light hasn't arrived. And because it moves at a finite rate, it might never get here, especially if the expansion of space outpaces it. Think about that for a moment. There are regions of the universe that may already be lost to us, not because they disappeared, but because their light will never reach our part of space. They might as well be gone. Not in reality, but in experience. They've crossed over into a kind of permanent invisibility, not darkness, but absence. This speed limit shapes everything. It's why we can only see part of the universe. It's why distant events seem frozen in time. It's why we look at ancient galaxies and see them not as they are, but as they were when light first left them. Some of those galaxies may not even exist anymore. They could have collided, changed, disappeared, but to us they still shine in the sky because their last message is still in transit. The speed of light also creates something called a light cone. Imagine a flash of light at a single point. That flash expands in a sphere, growing outward in all directions, limited by light speed. Everything inside that growing bubble could, in theory, be affected by the flash. Everything outside it is untouched. The same is true for every moment, every particle, every action. There's a limit to how far its effects can spread. Now reverse that. Look at your position here, now. The light cone reaching backward is made up of every event that could possibly influence you, and that cone has a boundary, the edge of the observable universe. Anything beyond it is outside your past light cone. It hasn't had time to touch you. Not yet. Maybe never. It's an elegant way to think about causality. What you see is not just determined by where you are, but by when you are. That timing is controlled by this simple, unchanging speed. Not the fastest we can go, but the fastest anything can go. There's something surprisingly calming about that. In a universe so vast where so much lies out of reach, there is still a kind of order, a limit we can understand, a structure that holds even as the universe expands, and the expansion matters here. Because while the speed of light is fixed, the space it moves through is not. That's what makes cosmic distances different from earthly ones. If you shine a flashlight across a room, the space doesn't stretch. But in the universe, as light travels, the space between source and destination stretches too. That's why objects can end up farther away than they seemed at first glance. That's why we can see galaxies that are now tens of billions of light years away, even though their light left when they were much closer. It also means the further back we look, the more redshifted that light becomes. Light from distant galaxies arrives stretched out, shifted toward the red end of the spectrum, not because it was emitted that way, but because space itself expanded while the light was in transit. It's not just a Doppler shift, it's a record of the growth of space itself, and this redshift is measurable. Scientists use it to determine how fast objects are moving away from us, and from that, how far they are. It's how we chart the universe, not with rulers, but with colour. So when you hear about the limits of observation, about what we can and can't see, it all comes back to this. The speed of light is the final gatekeeper. It's why some things are part of your universe, and others never will be. It's why the observable universe has a size, and why that size changes over time. In a few billion years, many of the galaxies we see today will have moved so far away that their light won't reach us anymore. The universe will still be full, but to future observers it will appear emptier, more isolated. The cosmic web will shrink, not in reality, but in visibility. That's one reason why we watch so carefully now. Every image from a deep space telescope, every spectrum, every map, they're snapshots of a universe that is slowly moving beyond our reach. Not because it's closing in, but because it's speeding away. So, as you rest here now, you're surrounded by light that has travelled for billions of years. It's arrived just in time. Some of it is already late, and some, from places beyond the horizon, will never come at all. And all of this, all of what you see and all of what you don't, is shaped by one constant. One simple rule, the speed of light. It sets the pace for every discovery, every limitation, every glimpse into the past. It defines the border between what is known and what is still waiting, beyond reach. From here, we'll move into what happens to light as the universe stretches. How distance isn't just measured in space but in time, and how the fabric of space itself tells light where to go and when to slow down. Not because it's resisting, but because the path itself is bending. But we'll take our time, there's no rush. The light isn't going anywhere, it's just arriving one photon at a time. You might picture space as a kind of emptiness, something passive, a backdrop that just sits there while stars and galaxies move across it. But space isn't still. It's not fixed. The more we study the universe, the clearer it becomes that space itself is doing something. It's growing. Quietly. Constantly. Without a center. Without an edge. It expands not into anything, but simply stretches everything that's already here. This idea might seem abstract at first, but it's one of the most important discoveries in cosmology. The universe is expanding. That's not a theory, it's a measurement. We see it in the way galaxies move, not because they're flying through space like rockets, but because the space between them is getting larger. The distances increase, even if the galaxies themselves are sitting still. This expansion was first observed in the 1920s. Astronomer Edwin Hubble noticed that the light from distant galaxies was shifted toward the red end of the spectrum. That redshift meant the galaxies were moving away, and the farther they were, the faster they seemed to be receding. That pattern didn't make sense if the universe was static, but it made perfect sense if space itself was expanding. Imagine dots on a balloon. If you blow up the balloon, the dots move apart, not because they're crawling over the surface, but because the surface itself is stretching. No single dot is the center. Every point sees every other point move away. That's how the universe behaves. Galaxies aren't flying through space away from some explosion. They're carried apart because the space between them is growing. Now, it's important to be clear. Not everything is expanding. Galaxies themselves aren't getting larger. Solar systems stay the same size. Even atoms remain stable. That's because local gravity, or other forces like electromagnetism, hold things together tightly enough to resist the pull. Expansion only becomes noticeable over huge distances, where gravity is too weak to counter it. Over time, this expansion shapes the large-scale structure of the universe. Galaxies drift apart. Clusters of galaxies move further from other clusters. Voids grow wider. The cosmic web, a massive, thread-like network of matter, stretches thinner. We still see it, but we see it changing. This stretching of space affects more than just distances. It affects time. It affects light. When light travels through expanding space, it stretches too. Its wavelength grows longer. That's the redshift we measure. Light that started out blue or ultraviolet might arrive here as infrared or even radio waves. The light hasn't changed on its own. It's been pulled by the space it moves through. That's why astronomers often describe the universe in terms of scale factor, a number that tells you how much the universe has stretched since a given moment. At the time the cosmic microwave background was emitted, the scale factor was about 1/1100 of what it is today. That means space has stretched over 1,000 times wider since then. Every photon from that early time has been pulled along with it. This expansion even shapes how we define distance. In cosmology, distance isn't always a simple number. There are different kinds. Comoving distance, proper distance, luminosity distance. Each one reflects a different way of measuring in a changing universe. It's not confusing just for fun. It's necessary because space is not static. A light beam that left a galaxy 10 billion years ago didn't travel a straight path through fixed space. It crossed a landscape that was changing as it went. You could say that space isn't like a road, it's like a moving sidewalk, or maybe a treadmill that speeds up as you run. The journey is shaped not only by where you go, but by how the ground beneath you behaves. That's how it works for light, for galaxies, for everything. And the rate of expansion hasn't been constant. For a long time, scientists assumed the expansion might slow over time. Gravity, they thought, would gradually pull things back together, maybe even stop the expansion entirely. maybe cause a collapse, a reversal. But in 1998, that idea changed. Astronomers studying distant supernovae found something unexpected. The light from these exploding stars suggested they were farther away than expected. That meant the expansion of the universe was speeding up, not slowing down. Space wasn't just stretching, it was accelerating. Galaxies weren't just drifting apart, they were being pushed. The cause of that acceleration was given a name: dark energy. It's not a substance we've detected directly. We don't know exactly what it is, but its effects are measurable. It accounts for about 68% of the total energy content of the universe. Not because we can see it, but because we can see what it does. It drives the expansion. It changes the fate of the cosmos. If expansion continues to accelerate, then the universe will become more and more empty over time. Galaxies will slip beyond our horizon. The night sky will dim, not because stars go out, but because the space between them grows too wide to cross. Light from distant sources will never arrive. Eventually, even nearby galaxies will move out of reach. And again, this isn't because things are flying away. It's because space itself is doing the work, quietly, continuously, unseen but unstoppable. In a universe without acceleration, you could imagine a future where we see more and more over time, where light from new regions arrives and the observable universe grows. But with accelerating expansion, that growth slows. There's a limit to what can ever become visible, a point beyond which galaxies are moving away faster than light can travel, not because they're breaking the speed limit, but because the road is stretching faster than light can cross it. This shapes what we know, what we'll ever know, and it's all tied to this one simple fact: space stretches. It's not always easy to picture. We think of space as an empty room, or a stage, or a blank canvas, but it's more like a medium that responds to energy and mass. Einstein's theory of general relativity tells us that mass tells space how to curve, and space tells mass how to move. But on the larger scales, it's not just curving, it's growing. You're not just sitting still on Earth. You're part of a system, inside a galaxy, inside a cluster, inside a universe that is expanding in every direction, not into something, just expanding. The distances between distant objects increase, the volume of space grows, and the rules of physics stay the same throughout, but their consequences change with scale. So the universe we live in is not a steady container, it's an active one, not static, but dynamic. And that changes what it means to look into the distance. You're not just seeing far, you're seeing through expanding space, and the light that reaches you has stretched to get here. Its wavelength, its energy, even its meaning. From here, we'll move into how that light changes, what it tells us about the earliest moments of the universe, and how we can use it to learn about regions we'll never reach. Because even though expansion puts some things out of reach, it also leaves behind a kind of fingerprint, a record we can read as long as we're paying attention. For now, just remember this: space isn't still, it's stretching, gently, steadily, not in a rush, not with noise, just part of the quiet rhythm of the cosmos. When we look into deep space, we're also looking back in time. That's not a metaphor, it's a direct result of how light works. The farther a galaxy is, the longer its light has been travelling. So when we observe the most distant objects in the universe, we're seeing them not as they are now, but as they were when their light began its journey toward us. There's a limit to how far that light can come, not because the universe ends there, but because the beginning does. The universe hasn't been around forever, at least not in the way we usually mean that word. It had a starting point, or more precisely a starting condition, about 13.8 billion years ago. That's when the expansion we talked about began. The moment time, as we understand it, got its first tick. Because of that, there's a maximum distance that light could have travelled to reach us. You might think that distance is 13.8 billion light-years, 1 year of travel for each year of the universe's age. But it's not that simple. Because space has been expanding all along the way, the objects that emitted the oldest light are now much farther than that. When we say the farthest light we'll ever see, we're not just talking about a long trip through space. We're talking about a trip through changing space. One of the most distant sources of light we can detect is the cosmic microwave background. It's the afterglow of the early universe, the light released when the cosmos was about 380,000 years old. Before that time, the universe was too hot and dense for light to travel freely. Photons bounced around constantly, unable to go more than a tiny distance before scattering off particles. It was like trying to shine a flashlight through fog, only much hotter and much thicker. But then, everything cooled, atoms formed, the fog lifted, and light began to move freely for the first time. That light is still travelling today. It's been stretched by expansion, redshifted into the microwave part of the spectrum, and it now surrounds us as a faint glow, not something you can see with your eyes, but something that sensitive instruments can detect from every direction. When we measure the cosmic microwave background, we're seeing the farthest light that has reached us. Not just far in distance, but far in time. That light left its source nearly 13.8 billion years ago, from a place that is now more than 46 billion light-years away. And even though the light is weak, cooled to just a few degrees above absolute zero, it carries with it an incredible amount of information. It tells us about the density of matter in the early universe. It shows us tiny fluctuations, small differences in temperature and energy that would later become the seeds of galaxies. It confirms that space was once filled with a nearly uniform glow, gently rippled by quantum noise stretched by inflation. This light is the oldest messenger we'll ever receive. Nothing before it could get through. There's no way to see farther back using ordinary light. Earlier times are hidden behind a kind of cosmic curtain, not because we lack the technology, but because transparency didn't exist yet. The universe, in those early moments, was opaque. There are efforts to look beyond the cosmic microwave background, not with light, but with other kinds of signals. Gravitational waves, for example, ripples in space itself, may have been created during the first fractions of a second after the beginning. If we can detect them, they could open a new window into the pre-light universe. But that's a different kind of observation. For light itself, photons travelling through space, the cosmic microwave background is as far back as we can go. As for the farthest galaxies we've observed, those come later. The James Webb Space Telescope and other deep sky surveys have pushed the limits of detection, finding galaxies that existed when the universe was just a few 100 million years old. These galaxies are incredibly distant. Their light redshifted to the point where it's no longer visible to the human eye. But the telescopes can still see it, in infrared. And what they show us is remarkable. Galaxies formed earlier than we expected. Stars began to gather and ignite in a relatively short time after the cosmic microwave background was released. Structures began forming quickly. Matter started pulling itself together under the force of gravity. These discoveries help refine our understanding of the early universe. They tell us how quickly things took shape, how long it took for darkness to become light. But even these far-off galaxies are nowhere near the limit of the observable universe. They are like islands inside a vast ocean. Beyond them, more galaxies exist. Galaxies whose light simply hasn't reached us yet or never will. You might wonder how we know they exist if we can't see them. The answer comes from what we do see. The distribution of galaxies, the patterns in the microwave background, the uniformity of physical laws. All of it suggests that space continues beyond the edge of our visibility. There's no reason to think the structure of the universe changes dramatically just beyond the horizon. No sign of a wall, no sudden drop-off, just more space. And because space expands faster than light can travel over great distances, there are regions from which light will never reach us. Not because it's too dim or too far behind, but because the expansion has pulled those regions away faster than the light can catch up. Those galaxies might have emitted their light billions of years ago, but the space between us and them has grown so much that the photons are lost, like a letter thrown into a river that flows too fast for it to reach the shore. That's what we mean by the farthest light we'll ever see, not just the most distant light today, but the limit of what light in principle can ever reach us from. The edge of the observable universe is not fixed. It grows as time passes. But even with that growth, the acceleration of expansion means there's a hard boundary, a maximum distance, a final frontier beyond which we will never receive a single photon. It's not that those places don't exist. It's just that their messages are travelling through a space that stretches too quickly. Every metre of progress they make is undone by expansion. Their light is trapped, not in darkness, but in distance. Still, the fact that we've seen as far as we have is extraordinary. We've captured light that's been travelling for nearly the entire age of the universe. We've mapped the sky as it looked billions of years ago. We've held in our instruments the faint echo of the earliest moments. Every telescope is a kind of time machine. Every image of a distant galaxy is a page from the past. And every step farther pushes the limit of human knowledge a little wider, even if the boundary of light stays in place. From here, we'll begin to look more closely at what that boundary means, not just as a distance, but as a concept. What does observable really mean? What lies just beyond that line, and how do we think about places we can't detect? Because even though the farthest light marks a clear line, the questions don't stop there. They never do. The word observable sounds simple. It suggests something you can see, or detect, or reach with the right tools. But in cosmology, it carries more weight than that. It defines the boundary between what we can confirm and what we can only imagine. It sets the outer edge of knowledge, not because our questions run out, but because the universe places a natural limit on what information can ever reach us. When we say observable universe, we're talking about the region of space from which light, or any other signal, has had time to reach us since the beginning. That boundary isn't marked by anything physical. There's no wall, no membrane, no shimmering surface. It's just a measure of distance, shaped by time and the speed of light within an expanding space. Right now, that boundary lies about 46 billion light-years away in every direction. It forms a sphere around Earth, not because Earth is at the centre of the universe, but because every observer, wherever they are, has their own observable universe centred on their position. From any point in space, the visible region is shaped by how far light has travelled to reach that point. It's a personal horizon, defined not by location, but by light's long journey. So observable doesn't mean visible to the naked eye. It doesn't even mean visible with a telescope. It means that in theory, given enough sensitivity, we could receive some kind of signal from that region. Light, radiation, gravitational waves. The tools don't have to exist yet. What matters is whether the signal had time to reach us at all. That's what makes the word so important. It doesn't describe what exists. It describes what we can interact with. It draws a line between the knowable and the unreachable, not because of our limitations, but because of the universe's structure. There's a temptation to think of the observable universe as a bubble floating in a larger unseen cosmos. That image isn't wrong, but it can be misleading. The universe may not be infinite, but as far as we can tell, it continues beyond our observable horizon. The physics doesn't change at the edge. The laws of nature don't fall apart just beyond our view. The patterns we observe, in matter, in radiation, in structure, all suggest that the universe outside our horizon is much like the part we can see. Still, we can't confirm that, not directly. That's what makes the term observable so precise. It doesn't claim that nothing exists beyond the horizon, only that we can't interact with it. No information from those regions has had time to reach us, and as expansion continues to accelerate, some of it never will. In practical terms, this means our understanding of the universe is always partial. No matter how advanced our technology becomes, no matter how long we wait, we will always be seeing just one portion of a much larger whole. Our measurements are based on light and data that are available here and now, and that availability is shrinking, not growing. Not because the universe is collapsing, but because it's expanding faster than light can keep up. That shrinking is subtle, but over cosmic timescales, it matters. Galaxies we can see today may slip out of reach in the far future. Their light will no longer arrive. They'll become part of the unobservable universe, not because they stopped emitting light, but because the space between us and them has stretched too far, too fast. It's easy to assume that the more time passes, the more of the universe we'll see. But that's only true up to a point. The observable universe grew rapidly in the early years of cosmic history as light from new regions reached us. But with the discovery of dark energy and the acceleration of expansion, that growth has slowed. There's now a maximum volume of space that will ever become visible. Beyond that, the rest of the universe will remain forever silent from our point of view. This doesn't mean we stop learning. The observable universe is enormous. It contains hundreds of billions of galaxies, each with billions of stars. It holds more than enough data to keep us studying for as long as we exist. But it does mean that some questions about the size of the full universe, about what might lie far beyond the horizon, can never be settled by observation alone. Instead, we use models, we use symmetry, we use assumptions based on what we see in every direction. And so far, what we see suggests uniformity. No strange edge, no unusual tilt, no center, just space, filled with galaxies stretching in every direction. There are also philosophical questions that come with this. If something is unobservable forever, does it belong to science? Does it count as part of reality? Or is it just a story we tell based on patterns? There's no single answer. Some scientists argue that testability is a core part of what makes a theory scientific. Others point out that if we have strong enough indirect evidence, it's reasonable to believe in things we can't see directly. We've done that before. We believed in atoms before we could observe them. We believed in black holes before we had pictures. But in those cases, evidence eventually arrived. For regions beyond the observable universe, it may never come. So the belief becomes probabilistic, not confirmed. A quiet kind of trust in consistency rather than proof. And yet, even within the observable universe, there's a vastness we're only beginning to explore. We've mapped a small portion of galaxies. We've studied only a few nearby clusters in detail. The cosmic microwave background gives us a full sky image, but it's only one moment in time. There's still so much to study within the horizon we do have. That's part of what makes the word observable so useful. It doesn't limit us. It defines our current reach and reminds us how much that reach depends on when and where we are. If we'd arrived earlier in the universe's history, our observable universe would have been smaller. If we arrive later, it may feel emptier, but for now, we're in a kind of middle ground, a time when much is still visible, but limits are beginning to appear. From here, we'll keep going deeper. We'll look at how time and distance work together in the universe, how light doesn't move in straight lines, and how even the shortest path is shaped by the curves and changes in the fabric of space. But for now, just consider what it means to observe, to detect, to measure. It's not about seeing with eyes. It's about receiving signals and understanding the journey those signals took to get here. And it's about recognizing that the edge of observation is not the end of existence. It's just the place where the light hasn't reached yet, and maybe never will. It's easy to imagine light travelling in a straight line. In daily life, that's how it seems to behave. A flashlight beam points forward. Sunlight casts a shadow. The path between source and receiver feels direct, uncomplicated. But in the universe at large, especially across billions of light years, the situation isn't so simple. Space isn't flat, time isn't separate, and light, while constant in speed, moves through a medium that bends and stretches with the presence of mass, energy, and expansion. To understand what we really see when we look deep into the universe, we need to think differently about time, distance, and the shape of space itself. Let's start with distance. In everyday terms, distance is just the amount of space between 2 points. A meter, a mile. Something you can measure with a ruler, or at least a map. But in cosmology, the concept of distance becomes more complicated. Not because scientists enjoy confusion, but because the universe does not stand still. As light travels, the space through which it moves expands. That means the path is changing beneath it, even as it moves forward. If a galaxy emitted light 10 billion years ago, the space between that galaxy and us didn't remain fixed. It grew. So while the light may have travelled for 10 billion years, the actual distance to that galaxy today is much greater than 10 billion light years, more like 25 or 30 billion, depending on the exact rate of expansion over time. That's why we don't talk about just one kind of distance in astronomy. There's look-back time, how long ago the light was emitted. There's comoving distance, the current distance to the source if we froze the expansion today. There's proper distance, the distance at a specific moment in cosmic time. And there's luminosity distance, a measure based on how dim the object appears, which accounts for redshift and energy loss. Each of these is useful in a different context. None of them fully captures the idea of distance the way we use it in everyday language. That's because in a curved, expanding universe, space and time are part of the same fabric. They aren't separate ingredients, they're part of a single geometry. That geometry is shaped by mass and energy. According to Einstein's theory of general relativity, any object with mass bends the space around it. Not like a dent in a surface exactly, but as a change in the way paths curve through space-time. Light follows those paths, not because it's being pulled like a ball on a string, but because those paths are the straightest possible routes in curved space. They're called geodesics, the equivalent of straight lines in curved geometry. If space were perfectly flat, light would move in what we'd call a straight line, but in the presence of gravity, or over great cosmic distances, those lines bend. We can observe this directly. One clear example is gravitational lensing. When light from a distant galaxy passes near a massive object, like another galaxy or a cluster, its path bends. The object acts like a lens, distorting the image of what's behind it. Sometimes the background galaxy appears stretched, or duplicated, or even formed into a ring. These effects aren't illusions. They're real shifts in the path of light caused by the shape of space itself. This tells us that light doesn't always travel in the way we might expect. If we were to trace its route across the universe, it would not form a perfect straight arrow. It would follow the terrain of space-time, a terrain shaped by everything it passes near. That includes visible matter, dark matter, and the overall curvature of the universe. And that curvature matters. Measurements of the cosmic microwave background and large-scale structure suggest that the universe is nearly flat, meaning that on the larger scales space doesn't bend dramatically, but nearly flat still allows for slight curvature, enough to matter over billions of light years, enough to shape the path of ancient photons. This also affects how we interpret time. We tend to think of time as a separate flow, moving forward at the same pace for everyone. But in relativity, time is affected by speed and gravity. The stronger the gravity, the slower time moves. The faster you go, the more time dilates. For light, which always moves at the same speed, these effects don't apply in the usual way. But for observers, they change how we measure everything. When we say that light has been travelling for 13 billion years, we're speaking from our frame of reference. From the perspective of the photon itself, if we could imagine such a thing, no time has passed. The journey is instantaneous. That's not just poetic, it's a consequence of relativity. Time and space collapse into a kind of zero interval at the speed of light. From our side, it's billions of years. From the light's side, it's a single moment. This contrast reminds us that time and distance aren't universal constants. They depend on the observer, on the frame, on the geometry of space-time. That's why cosmologists use models, not just maps but equations, to calculate what we see and when we see it. Those models take into account the expansion of space, the curvature of light paths, the slowing and speeding of time, and the structure of the universe itself. Even the idea of now becomes fuzzy on large scales. What does it mean for a galaxy 10 billion light-years away to be doing something right now? The light we see from that galaxy is 10 billion years old. We have no way of knowing what's happening there at this moment. Our view is stuck in the past, and the farther we look, the deeper into history we go. There is no universal clock ticking across the universe. Time is local, defined by gravity, velocity, and perspective. That doesn't mean the universe is chaotic. It means the structure is more complex than our daily experience suggests. This is part of why building a model of the universe is so difficult. Observations must be untangled from the effects of distance, motion, and curvature. We can't just look and measure. We have to interpret. We have to understand the journey that light took, how long it travelled, how far space stretched while it moved, how gravity bent its path, and how redshift altered its energy. All of this makes cosmology more than a study of distant stars. It's a study of how signals move through a dynamic, flexible medium. It's about tracking the relationship between light, space, and time, not as separate things, but as one unified structure. From here, we'll begin to examine what that oldest light actually tells us, not just how far it came, but what it reveals about the earliest state of the universe. Because buried in the faint signals of ancient photons are the clues to where everything started, and maybe how it will end. But for now, it's enough to understand that when you look into the sky, you're not seeing a flat surface. You're seeing through time across expansion and along curved paths shaped by gravity and motion. What reaches you is a result of countless interactions between light and the structure of space itself. And even though those paths are complex, the end result is simple. Light finds its way, slowly, carefully, one photon at a time. If you were to turn off every star, every planet, every glowing object in the universe, if you shut down galaxies and black holes and all the flickering light across space, there would still be something left. A faint hum. Not a sound exactly, but a kind of glow. It's everywhere. It doesn't come from a direction. It isn't local. It surrounds us in all directions at all times. Even in the darkest corners of space, it's there. Gentle, constant, ancient. We call it the cosmic microwave background. But some people just call it the afterglow. Others call it a whisper, a signal so soft and so old that it took us nearly 14 billion years to hear it properly. But once we did, it changed everything we thought we knew about the universe. This light is the oldest thing we can observe. It comes from a time long before stars formed, long before galaxies began to take shape, long before the universe looked anything like it does today. The microwave background comes from a moment just 380,000 years after the Big Bang, when space was still glowing, but finally cool enough to let light move freely for the first time. Before that moment, the universe was filled with a hot, dense plasma, a kind of fog of particles and radiation. Photons couldn't travel very far before bouncing off electrons. The entire universe was opaque, like a thick soup of energy. But as things cooled, electrons began to combine with protons. Atoms formed. Suddenly the fog cleared, and light was free to move. That light, that very first light, is still travelling. It's not bright. It's not in the visible spectrum anymore. Over billions of years, the expansion of space has stretched it out. Wavelengths that once glowed in ultraviolet now lie deep in the microwave range. The temperature of this light is only about 2.7 Kelvin, just a few degrees above absolute zero, but it's still there, still detectable, still speaking. The cosmic microwave background, or CMB, was first detected in 1965, almost by accident. Two radio engineers, Arno Penzias and Robert Wilson, were trying to eliminate noise from a sensitive antenna, but the noise wouldn't go away. It came from every direction. No matter where they pointed the dish, the signal stayed the same. Eventually they realised it wasn't noise at all. It was the echo of the early universe. That discovery earned them the Nobel Prize. But more importantly, it gave cosmologists something they had never had before: direct evidence that the universe had a beginning, that it had been hotter, denser, and smaller in the past. The microwave background was a snapshot, a record of what the universe looked like when it first became transparent, a picture, frozen in time, of the entire cosmos as an infant. Since then, we've mapped the CMB in extraordinary detail. Satellites like COBE, DBMAP, and Planck have measured its tiny fluctuations, slight variations in temperature and density scattered across the sky. These variations are tiny, just 1 part in 100,000, but they hold the seeds of everything. The patterns of the microwave background tell us where matter began to clump together, where galaxies would eventually form, where voids would open. It's strange to think that the structure of today's universe, the web of galaxies and clusters and filaments, all started with tiny ripples in this ancient light. But those ripples weren't random. They came from quantum fluctuations in the very early universe, fluctuations that were stretched and amplified during the period of inflation. So when we look at the microwave background, we're not just seeing the first light, we're seeing the fingerprints of physics from a time before light could even exist. We're seeing the subtle imprints of inflation, of quantum mechanics, of the earliest forces shaping reality. And the uniformity of the CMB is remarkable. No matter where we look, it looks almost exactly the same. That tells us something profound, that the early universe was smooth, balanced, homogeneous, at least on large scales. The temperature differences are real, but they're tiny. That balance is what allowed the universe to evolve in the way it did, not into chaos, but into structure. There's also information in the polarization of the light, in the way it was scattered, in the direction it was moving when it last interacted with matter. We're still learning from that, still squeezing data out of those ancient photons. Every pixel, every subtle shift in temperature or orientation helps refine our understanding of cosmic history. But even more than the data, there's something quiet and grounding about the fact that this light is always with us. No matter where you go, to the farthest reaches of space, to the emptiest void between galaxies, the microwave background is there. It's not loud. It doesn't interfere with life or block our view. It's just always present. A faint whisper from a time before anything we know today had formed. And it's not slowing down, it's still moving, still expanding. Its wavelengths are still stretching as the universe grows. That means it's getting colder, fainter, harder to detect. In the far future, trillions of years from now, civilizations might not even be able to find it. The signal will be too weak, the expansion too wide. The past will fade into undetectability. But we're here now, in a time when we can still hear it, still measure it, still study it, and the more we do, the more we learn, not just about how the universe looks, but how it began, what it was made of, how it evolved, and what its future might hold. This background light is like a memory, not of something personal, but of something shared by every part of space, every galaxy, every atom, every observer, no matter where they are. We all carry the imprint of that early glow. It's not behind us, it's around us. From here, we'll explore what came after, how the first stars lit up the darkness, how structure formed, and how the visible universe began to take the shape we see today. But even as we look ahead in time, that quiet light stays with us, just behind everything, softly reminding us of how it all began. Before the cosmic microwave background was released, before atoms formed, before light could move freely, the universe was already busy. In fact, the most dramatic transformation in the history of the cosmos may have happened in the first fraction of a second, not slowly, not gradually, but in a burst so fast and so extreme that it set the scale for everything that followed. This idea is called inflation. It's a theory about the first instant after the beginning, not the Big Bang itself, but the moment just after, when the universe was still unimaginably small, but suddenly and rapidly expanded. Inflation wasn't part of the original Big Bang model. It was introduced later, in the 1980s, to solve some puzzles that didn't quite fit. One of those puzzles was the uniformity of the cosmic microwave background. No matter which direction we look, the temperature of that light is almost exactly the same. But if the universe started expanding slowly, then distant regions shouldn't have had time to communicate, to even out their differences. They should have been causally disconnected. Yet they aren't. Inflation solves that by saying the universe began in a tiny connected region. Everything was in contact, and then, in a fraction of a second, that region stretched far beyond what we can see. Tiny differences were smoothed out. Space expanded so quickly that it looked uniform everywhere. That's why the microwave background is so consistent. Inflation stretched a tiny balance patch into a vast observable cosmos. And when we say inflation was fast, we mean fast. The theory suggests that the universe expanded by a factor of at least 10^26 in less than a trillionth of a second. That's not something we can see directly. But its consequences are written into the structure of space. Quantum fluctuations, tiny, random variations in energy, were present in that early moment. Normally, those fluctuations would have stayed microscopic. But inflation magnified them. It took small differences and blew them up to cosmic scales. Those variations became the seeds of structure, the places where matter would later clump together, the regions that would grow into galaxies and clusters and voids. So when we look at the sky today and we see galaxies arranged in filaments, or the subtle patterns in the cosmic microwave background, we're seeing the fossilized imprint of inflation. We're seeing a map of randomness stretched across billions of light years. Inflation also helps explain why the universe looks flat. In geometry, space can be curved, positively like a sphere, or negatively like a saddle. But all our measurements suggest that the universe is almost perfectly flat. That kind of flatness would require a precise balance of energy in geometry, unless something happened to enforce it. Inflation enforces it. Just as a balloon becomes flatter and flatter on its surface the more you inflate it, the rapid expansion of the universe would flatten any initial curvature. It doesn't matter what the shape was at the start. Inflation would have smoothed it out. That's why space looks Euclidean, even though its birth was chaotic. There are other clues that point toward inflation. The distribution of galaxies, the statistical patterns in the microwave background, the near-scale invariance of fluctuations, meaning the differences in temperature look the same across a wide range of sizes. These are not accidental features. They're expected outcomes of inflation. But as much as inflation explains, it also raises questions. What caused it to start? What caused it to stop? We don't fully know. The idea is that some form of potential energy, sometimes described as a false vacuum, temporarily dominated the universe. That energy drove the expansion, and when it decayed, inflation ended. The energy converted into particles and radiation, filling the universe with matter and heat. That transition is called reheating. From that point on, the universe continued to expand, but much more slowly. Matter began to cool, atoms formed, light was released, and the more familiar stages of cosmic evolution began. But the blueprint had already been set. Inflation laid the foundation. There's also a deeper implication. If inflation happened once, it might happen again, or might never have truly ended in all places. Some versions of the theory suggest that while inflation stopped in our region, it continues elsewhere. That leads to a concept called eternal inflation, in which different regions of space stop inflating at different times, creating pocket universes. Some might be like ours, others might follow different rules. This idea is one path to the multiverse, not in the sense of alternate timelines, but as an endless collection of regions, each with its own properties, each causally disconnected from the others. We can't see them, we can't reach them, but they could still exist, expanding beyond our horizon, forever. It's important to be cautious here. Inflation has strong support, but the details are still under investigation. There are many models, some are more consistent with observations than others, and there's no direct way to see inflation itself. We see its aftermath, its shadow, its effects. One way scientists hope to probe it further is through gravitational waves. Inflation should have produced a background of ripples in space-time, tiny waves left over from the violent stretching of the early universe. If we can detect those, they could confirm inflation and even help us understand the energy scale at which it occurred. But so far those waves remain elusive. The instruments are sensitive, but the signal is faint. We're still looking, still refining the models, still comparing predictions with data. None of this changes the fact that inflation, as an idea, is powerful. It ties together multiple threads: the uniformity of space, the flatness of the universe, the origins of structure. It takes a moment that lasted less than a blink and shows how that moment became the canvas for everything we see. It's a reminder that time and scale are not always what they seem, that the most meaningful events in cosmic history may have taken place before light, before matter, before even the concept of before had time to settle. From here, we'll step out of those earliest instants and return to the wider question, whether the universe has edges, whether it loops back on itself, or whether it simply goes on without boundary. Because even if inflation shaped what we see, it may have left us inside a space that's far larger than we can ever measure. But we don't need to rush there just yet. We've already gone back as far as light and theory will take us, to a time when space itself expanded faster than any light could travel. And from that expansion came everything, including us. When we think about the universe, it's easy to picture it like a thing, an object, maybe round or flat or dome-shaped, floating somewhere, with an inside and an outside. And like any object, it might feel natural to ask, does it have an edge? Is there a boundary? A place where the universe ends? It's a reasonable question. In fact, it's one of the oldest. For as long as people have looked up, they've wondered what lies beyond the stars and whether the sky's just a ceiling, something with a limit. But when we start to understand space through physics and observation, the idea of an edge begins to mean something different. The universe does not appear to have an edge in the usual sense. There's no wall, no barrier, no outer shell where everything stops. If you were to travel in a straight line through space, assuming you could go on forever, you wouldn't hit anything that says, this is the end. Space simply continues. Or it wraps, depending on its shape. Either way, there's no fence, no drop-off, no outer boundary where space ends and non-space begins. This is true even though the universe had a beginning. That might sound contradictory at first. How can something have a beginning but no edge? But the beginning of the universe wasn't like the explosion of a firework into empty sky. It wasn't an event inside space. It was the origin of space itself. That means the universe didn't expand into something. It didn't push into empty surroundings. It was, and is, everything. Space expanded within itself. That expansion continues, but not into a larger arena. It's just more distance opening up between things. The universe isn't growing like a balloon in a room. It's more like the surface of the balloon itself, expanding in all directions with no point being the centre and no edge to fall off. Now, when we say the universe doesn't have an edge, we're talking about the observable portion and what it seems to be a part of. Remember, the observable universe is finite. It's a sphere centred around us, about 93 billion light-years across. But that's not the whole universe. It's just the part we can see. Beyond it, we have reason to believe space continues. The key idea here is that space can be either infinite or finite but unbounded. An infinite universe is just what it sounds like. It goes on forever with no repetition, no end, no wraparound. A finite but unbounded universe is trickier. It's a space that loops back on itself, like the surface of a sphere. If you travel far enough in one direction, you eventually end up where you started. Not because you hit an edge and turned around, but because space itself curves and connects. We live on the surface of a planet, and we accept that we can walk in any direction without finding an edge. That surface is finite in area but has no boundary. The same could be true for three-dimensional space. It might be curved in such a way that it closes on itself. Finite, but edgeless. So which is it? Is the universe infinite, or is it wrapped? At this point, we don't know for sure. Observations of the cosmic microwave background suggest that space is very close to flat, which would allow for either possibility. If it's exactly flat and continues that way forever, then the universe may be infinite. If it's slightly curved, it might loop back. But the curvature, if it exists, is so small that we haven't detected it. Our instruments measure with increasing precision, and they tell us that space is either infinite or so vast and subtly curved that for practical purposes it might as well be. This is different from an edge. Curvature is a property of space itself. An edge would be something that space ends into, and that doesn't match what we observe. There's no sign that galaxies become less common or distorted near some border. No asymmetry in the background light. No gradients that would suggest we're close to a boundary. And there's a deeper issue. If the universe had an edge, what would be beyond it? If space ends, what does it end into? The very idea assumes some kind of container. But the universe isn't inside anything. Space is the container. There's no outside. At least not in any meaningful way that we can observe or describe. Even in theories where space is embedded in a higher dimension, like in some versions of string theory, those extra dimensions don't behave like directions we can travel. They're mathematical features, not physical escape routes. They don't offer an outside we can reach. They're part of the model, not a place beyond the edge. There are also ideas from inflation that suggest our observable universe is just one patch of a much larger whole. If eternal inflation is correct, there could be an endless collection of regions like ours, each with its own version of the Big Bang, each with its own properties. But even there, no edge in the usual sense exists. Just a fractal-like structure that grows endlessly, never stopping, never closing off. So when we ask whether the universe has an edge, we have to be careful with what we mean. If we're asking whether the observable universe has a boundary, the answer is yes, defined by light and time. If we're asking whether space itself has a border, the answer appears to be no. That might feel unsatisfying at first. We're used to things ending. We like boundaries. They give shape to experience. But the universe doesn't need that. Its shape can be vast or looping or infinite, and still consistent with everything we observe. And maybe that's the most honest answer we can give. There is no edge in the way we expect. No wall. No stopping point. Just more space, or curved space, or structure that extends beyond our reach. From here, we'll begin to explore what that beyond might be. Not as a hard line, but as a region outside the observable sphere, a space that exists even though its light hasn't reached us, and never will. We'll ask what we can infer about that unobservable realm, whether it looks like this one, whether it changes, and whether it includes possibilities far beyond what we can imagine. But for now, it's enough to know this. If you travelled in a straight line through space, you wouldn't find an edge. You'd find more space. Or maybe you'd return to where you started. Either way, the journey would continue. Quiet, wide, and open. If the observable universe is only a piece of something larger, then it's natural to wonder what the rest of it looks like. Not just in theory, but in practice. If we could step outside our light horizon, not with a spacecraft, but somehow with information, what would we find? We don't have access to that region. Its light has never reached us, and some of it never will. But we can still ask the question, because physics isn't just about observation, it's also about inference, using what we do see to make reasonable guesses about what lies beyond. The first assumption, and the simplest, is that the universe continues more or less the same way. That space beyond the observable region looks a lot like space inside it. Same laws of physics, same cosmic background, same kinds of galaxies scattered across the same expanding web, no abrupt change, no hidden edge, just more of what we've already mapped. This is called the cosmological principle. It states that on large enough scales the universe is homogeneous and isotropic, meaning it looks the same in all directions and from all locations. It's not a law of nature, it's a working assumption based on the fact that the observable universe follows this pattern with impressive consistency. Every patch of sky shows similar properties. No matter where we look or how far, the rules seem to hold. That doesn't mean there are no local differences. Galaxies form clusters, structures vary, but the overall average, the large-scale picture, stays remarkably stable. That's one reason scientists feel comfortable saying the unobservable universe probably resembles the part we can see. But we can also imagine alternatives, because even if the laws of physics are the same everywhere, the outcomes might not be. Tiny quantum fluctuations in the early universe could have created differences, regions where matter clumped differently, or where galaxies formed later, or where no galaxies formed at all. Inflation, especially if eternal, would allow for that. It could create a patchwork of regions, each with slightly different initial conditions. Some might be denser, some emptier, some shaped by rare early events, and that's still within a framework of familiar physics. But there are also models that go farther. In some versions of eternal inflation, the universe is made up of many disconnected regions, each effectively its own universe, not just different in detail but in fundamental constants. One might have stronger gravity, another might lack the conditions for atoms to form, another might have no stars at all. These aren't universes in separate dimensions, they're separate zones within a larger inflating space. Each one undergoes its own Big Bang-like process, forming its own observable universe. These regions are so far apart, and the space between them expands so quickly that they can never communicate, not even in principle. From our perspective, these ideas are difficult to test. We can't see those other regions. We can't interact with them. They're part of what's called the unobservable universe, not just temporarily hidden, but permanently beyond reach. Still, the theory that produces them, eternal inflation, has strong internal logic. It fits well with what we see in the microwave background. And if inflation happened once, there's no reason to assume it only happened here. So the question becomes, is the rest of the universe just more of the same? Or is it more than that? A diversity of regions, each with different properties, each isolated by expanding space. Some scientists approach this by looking at probability. If the inflationary model suggests a wide range of possible conditions across different regions, then we might live in the kind of region where conditions allow observers like us to emerge. That idea, called the Anthropic principle, doesn't predict what we'll see, but it can help explain why we see certain things and not others. For example, if dark energy had been much stronger, the universe might have expanded too quickly for galaxies to form, but it wasn't. And here we are. This doesn't mean the universe was designed for us. It means that in a vast range of possibilities, we happen to be in one that permits complex structures. And that might explain why the part we can see has the values it does. There are other ideas as well. Some suggest that the universe is finite but much larger than what we observe, perhaps curved or topologically connected in ways we don't yet detect. Some speculate that relics of other regions might leave subtle imprints, cold spots in the microwave background, or unexpected alignments in galaxy distributions. So far, no clear evidence supports that. But the search continues. Others wonder if we might detect gravitational waves from beyond our horizon. or if quantum entanglement could somehow stretch across regions. These ideas are interesting but speculative. They remain on the edge of theory, not yet anchored by observation. The truth is, the universe may be bigger, stranger, and more varied than we'll ever directly confirm. But that doesn't mean the question is empty. Every measurement we make, every improvement in precision, helps us rule out certain models and strengthen others. We narrow the possibilities, we refine the picture. And in doing so, we learn more about what it means to live in a universe with a horizon, a boundary not of space, but of information. It's worth remembering that for most of history, even the next valley was unknown. People looked at the stars and wondered if they were close or far, if they were part of the sky or something more. We've answered many of those questions. Now we face a similar horizon, only this one is 46 billion light-years wide and growing. From here, we'll look more closely at the future, how the accelerating expansion will change what's visible, how cosmic isolation may increase, and what kind of universe lies ahead for the distant descendants of galaxies and stars. But for now, even as we sit inside our limited sphere of light, we can be fairly certain we're not alone in space, not in the sense of other civilizations, though that remains an open question, but in the sense that our region is just one part of a much larger whole, a structure we may never see, but one that continues just beyond the edge of light. The word infinite carries weight. It suggests something without limits, no edges, no end, no final count. When we talk about infinite space, it means more than just really big. It means unbounded. Not just more galaxies beyond our view, but an endless number of them. Not just stars we haven't seen, but stars no one ever will, stretching out in all directions forever. It's a concept that's hard to hold in the mind. Infinity isn't just unfamiliar, it's abstract. We don't experience it directly. Everything in our lives has a size, a duration, a number. So when we ask if the universe is infinite, we're really asking whether reality itself extends beyond every possible horizon, without repeating, without curving back, without ever stopping. The short answer is, we don't know, but we do have models, and we have observations, and from those we can explore what it would mean for the universe to be truly infinite, or whether that feeling of endlessness is just an illusion created by the limits of what we can measure. First, it's important to distinguish between the observable universe and the full universe. The observable universe is a sphere centered on Earth, roughly 93 billion light-years across. That's as far as light has been able to travel since the Big Bang, given the expansion of space. But it's not a physical boundary. It doesn't mark the edge of existence, it marks the edge of our visibility. The universe could be much larger than that, or it could be infinite. When we look at the data, especially the detailed measurements of the cosmic microwave background, we find that space appears to be flat. That is, it doesn't curve in on itself like the surface of a sphere, and it doesn't bend outward like a saddle. In flat space, parallel lines stay parallel, and triangles behave the way they do in high school geometry. That flatness is important. In general relativity, the shape of space is tied to its energy content. A universe with too much matter would eventually recollapse. A universe with too little would expand forever, but in a way that creates noticeable curvature. A flat universe sits right in between, perfectly balanced. Current observations suggest that space is flat to within a small margin of error. That means two things. First, the universe might be infinite, because flat space, unless it's wrapped or curved in a subtle way, doesn't require a boundary. Second, even if the universe isn't infinite, it must be much larger than the part we can observe. Otherwise, we'd see curvature, and we don't. So, from a measurement perspective, space either goes on forever, or it's so vast that the difference is practically meaningless to us. We can't reach the edge. We can't see the end. All we see is more space, more structure, more of the same. Still, an important distinction remains. Just because something appears infinite doesn't mean it truly is. The illusion of infinity can come from a lack of boundaries, or from shapes that loop without edges. The surface of the Earth, for example, feels endless if you keep walking. You never find a wall, but it's finite. It wraps. The same could be true for space. There are ways to model a finite universe with no edge. Topologies that allow space to connect back on itself in 3 dimensions, like a 3D version of a torus or a more complex shape. In such models, space is limited in volume but without any borders. If you could travel fast enough and far enough, you might eventually return to where you started, not by turning around, but by moving forward in a straight line. If that's the case, then we wouldn't need an infinite universe to explain what we observe, just a very large one. Large enough that light hasn't had time to wrap around. Large enough that the repetition, if it exists, is beyond detection. There have been searches for evidence of this, signs that the cosmic microwave background might repeat, or that the same galaxies could appear in different directions. So far, nothing conclusive has turned up. But the limits of detection mean we may never know for sure. And there's another layer to the question. Even if space itself is infinite, the contents of space may not be. Matter, energy, galaxies, these might only fill a portion of an endless void. Or they might repeat, in patterns shaped by physics. If the universe is infinite and uniform, then every possible configuration of matter must happen somewhere, just by chance. That's a strange implication. It means somewhere out there could be a region exactly like this one. A copy of the Earth, a copy of you. Not from science fiction, but from probability. That kind of thinking leads into the idea of the infinite multiverse, where not only space but possibility is unbounded. But again, we're deep into speculation. There's no evidence for these duplicates, no way to detect them. Just a logical consequence of an infinite, statistically uniform space. And there are philosophical questions too. Is an infinite universe really knowable? Can anything truly infinite exist in physical reality? Or is it just a mathematical construct, useful for equations, but not something the cosmos actually delivers? Some physicists are cautious about infinity. They treat it as a sign that a model has been pushed too far. Others accept it as a natural outcome of how space behaves. There's no consensus, and that's because we're dealing with a kind of boundary that isn't physical, a boundary of knowledge, of inference, of what it means to ask about the whole of reality when we only live in one small patch of it. What we can say is this: from everything we observe, space appears to continue smoothly. There's no visible edge, no sign of a stopping point. If the universe is finite, it's far larger than the part we can ever see. If it's infinite, it includes more stars, more galaxies, and more possibilities than we can begin to grasp. From here, we'll start to look forward again, not just into space, but into time. We'll ask what happens to the universe as it continues to expand, what happens to light, to matter, and to visibility itself. Because even if space is infinite, our view of it is shrinking, and that has consequences for the future of knowledge and the fate of everything we can see. If space might be infinite, and if inflation can generate vast regions beyond our view, then it's natural to take the next step and ask, could other universes exist? Not just distant parts of this one, not just galaxies too far away for light to reach us, but entirely separate domains, places with their own physics, their own timelines, their own versions of reality. It's a question that science didn't always ask seriously. For a long time, the word universe meant everything, the totality. By definition, there was only one. But as theories expanded and as models like inflation matured, that assumption began to shift. The word universe now sometimes refers to a local region, one bubble in a larger structure. And the idea of a multiverse has entered serious discussion, not as a science fiction device, but as a possible consequence of well-established physics. The simplest path to other universes comes from inflation. In some versions of the theory, inflation doesn't end everywhere at once. Instead, it ends in patches. Each patch stops inflating and becomes a bubble universe, like ours. But between these bubbles, inflation continues, driving space to expand even more. Over time, more and more bubbles form, each causally disconnected from the others, each with its own starting conditions. This is called eternal inflation. It doesn't require new physics, just a certain kind of inflationary field that decays in a slow and uneven way, and once it starts, it never stops completely. Inflation continues forever, even while local universes like ours appear and evolve. In this picture, what we call the universe is just one bubble in a vast foaming sea, and if the inflationary model is correct, then this structure might be inevitable, not just possible, but expected. Still, we have to be careful. These other universes would be unreachable. The space between them expands too fast. No light, no signal, no information can ever pass from one bubble to another. That makes them unobservable, not just in practice, but in principle. Which raises the question, can science describe what it can't test? The answer depends on how we define theory. If a model makes predictions about our own universe, and those predictions match what we see, then the model gains credibility, even if it includes features we can't observe. For example, if inflation predicts a multiverse, and inflation also explains the patterns in the cosmic microwave background, then the multiverse becomes a reasonable implication, even if it's not directly testable. That's where things stand now. Some cosmologists are comfortable discussing the multiverse as a consequence of inflation. Others remain cautious, preferring models that stay strictly within observational limits. There's no consensus, but there's ongoing work. Trying to refine the theories, test their predictions, and find any indirect signs that might support or challenge the idea. Beyond inflation, there are other ways multiple universes could arise. One comes from quantum mechanics. In the many worlds interpretation, every quantum event with multiple possible outcomes gives rise to all outcomes, each in its own branching timeline. According to this view, reality constantly splits, forming a vast growing tree of parallel worlds. In one, a particle goes left. In another, it goes right. And both branches continue, unaffected by each other. This version of the multiverse is very different from the inflationary kind. The universes don't exist far away in space. They exist in a kind of abstract configuration space. They're not separate bubbles, they're parallel states, all evolving from a shared quantum wave function. Again, there's no way to interact with these other versions, no crossover, no communication. But some physicists find the many worlds interpretation elegant, because it removes the need for measurement to collapse a quantum state. Everything evolves deterministically. It's just that the observer is always embedded in one path, unaware of the rest. There are also ideas from string theory that suggest the possibility of multiple universes. String theory allows for many possible configurations of extra dimensions and physical constants. Some versions estimate that there could be 10,500 different stable solutions, each corresponding to a different kind of universe with different laws. This is sometimes called the string landscape. If that landscape is real, and if eternal inflation selects different points on it in different regions, then the multiverse becomes even more varied. Some universes might be lifeless, some might expand too quickly, some might never form atoms, a few might resemble ours, and only those few would contain observers asking these questions. This leads back to the Anthropic principle. The idea that we observe this kind of universe because it's the kind where observers can exist, not because it's special, but because it's compatible with life. If there are many universes, each with different parameters, then it's not surprising that we find ourselves in one that works. Still, this raises deep questions. If something exists beyond our universe but leaves no trace, can we say it's real? If we can never test or falsify it, is it part of science or philosophy? Some researchers argue that the multiverse is just a logical extension of current models. Others see it as a sign that our models are incomplete. The debate isn't just about physics, it's about what counts as a valid explanation, what it means to know something, what role evidence plays when we can only ever access one small patch of reality. But even with those uncertainties, the idea of other universes continues to shape how we think about the cosmos. It reminds us that our view may be limited not just by distance but by structure, that the rules we observe may not be the only ones that exist, that our observable universe may be one region in a much larger and more varied system, a system we can't leave but can still try to understand. From here, we'll turn back toward our own patch of space and time. We'll explore how the expansion of the universe affects what we see, what we'll continue to see, and what might someday fade from view forever. But for now, it's worth considering. The space we know may not be all there is. The universe we live in may be one of many, and even if we never see the others, the fact that they're possible changes the meaning of everything we call the universe. As the idea of the multiverse has moved from fiction into physics, it's brought with it a different kind of question. Not just could other universes exist, but should we treat them as science? If a theory includes things we can't observe, does it still belong in the same category as gravity, electromagnetism, or dark matter? This question matters. It shapes how theories are built, how evidence is judged, and what it means to explain the universe in scientific terms. And while the word multiverse can sound like a story, expansive, imaginative, even fantastical, it sits at the edge of some very serious thinking. The question isn't whether the idea is exciting, it's whether it's necessary, whether it follows logically from what we already know, and whether it can be tested in any meaningful way. Let's start by looking at where the idea comes from, not in speculation, but in models that were developed to explain real, observable features of the universe. In cosmic inflation, the multiverse isn't added for drama. It's a direct consequence of how certain versions of inflation work. If inflation doesn't end uniformly, but continues in patches, then the result is a growing landscape of bubble-like regions, each disconnected from the others, each evolving its own way. The same equations that explain the smoothness and flatness of our observable universe also suggest that it's just one region among many. Likewise, in quantum mechanics, the many worlds interpretation was created to solve a practical problem. What happens when a quantum system is measured? Rather than collapsing into a single result, the full wave function continues to evolve. Every possible outcome persists, but in a non-interacting branch. This wasn't introduced as a fantasy, but as a way to keep the mathematics consistent and avoid ad hoc rules. And in string theory, the multiverse appears not because anyone wanted it to, but because the equations allow for a huge number of stable configurations. Different shapes and sizes of extra dimensions lead to different physical constants, and if the universe samples this landscape through inflation, then many kinds of regions can emerge. So the idea of multiple universes isn't a separate story layered on top of science. It comes from within the theories themselves, from attempts to explain what we observe using the best tools we have. The tension arises when those tools reach beyond what we can test. Science is built on observation, hypotheses are tested, predictions are compared to data. But what happens when a theory makes good predictions for the things we can see, and also includes things we can't? Do we accept the unobservable consequences, or draw a line? Some argue that if a model works well where it can be tested, then we should take its full implications seriously. If inflation explains the structure of the universe and the patterns in the cosmic microwave background, and if that same model predicts a multiverse, then the multiverse is part of the package. Ignoring it selectively would be inconsistent. Others caution that untestable predictions can't be part of science. They might be part of philosophy, or mathematics, or even informed speculation, but if they can't be confirmed or falsified, They don't belong in the same category as testable theories. From this perspective, science stops at the edge of the observable. There's no simple resolution. The debate touches on the philosophy of science as much as the content of physics. It asks what counts as evidence and whether indirect support, like a theory's success in other areas, is enough to justify belief in its broader claims. Even within the physics community, views vary. Some researchers work directly with multiverse models, others avoid them entirely. Some see them as inevitable outcomes of solid theory, others treat them as placeholders, useful for discussion but not final explanations. There's also the issue of probability. If a multiverse exists, and if all possible values for physical constants are realized somewhere, then explaining why our universe has the properties it does becomes a different kind of question. It's no longer about why this value of dark energy exists, but why we observe it. And the answer becomes statistical. Out of all the universes, only some will allow stars and galaxies to form. We live in one of those because observers can only arise in regions where the conditions are right. That kind of reasoning makes some people uneasy. It feels less like an explanation and more like a selection effect. It shifts the question from physics to statistics, and that shift isn't satisfying for everyone. Still, it's a valid way to reason, especially in the absence of other constraints. If you can't change the setup, and if you have many outcomes, then probabilities matter. But it changes the flavour of cosmology. It becomes less about finding the answer and more about mapping a space of possible answers and understanding why we find ourselves where we do. And then there's a practical side. Even if we can't observe other universes directly, there might still be indirect consequences. Some versions of the multiverse predict collisions between bubble universes. If that happened early enough, it might leave a signature in the cosmic microwave background, a distortion, or an unusual alignment. So far, no clear evidence of that kind has been found. But the search continues. There's also the possibility that future theories, more complete than the ones we have now, might offer ways to test the multiverse idea more directly, or might rule it out entirely. Our understanding of space, time, and quantum fields is still evolving. New instruments, new observations, or new theoretical breakthroughs could change the picture. Until then, the multiverse sits in a kind of boundary zone. Not pure speculation, but not fully grounded either. It's a serious topic in cosmology, rooted in mainstream theories, but still waiting for confirmation. It challenges our definitions. It expands what the universe might mean. And it reminds us that the border between science and story isn't always sharp. From here, we'll shift back toward what we can measure more directly, the shape of space itself, whether the universe is open or closed, whether it curves inward, outward, or remains flat across scales. Because even if we don't yet know how many universes might exist, we can still learn more about the one we're in. If the universe has no edge, and possibly no end, then the next question becomes not, how far does it go, but what shape does it take? Not in the sense of what it looks like on the outside. There is no outside, but in terms of how space behaves within itself, how lines move, how geometry works, how gravity and distance interact on the larger scales. In cosmology, space isn't just an empty container, it has structure, it can curve, and that curvature, even if very subtle, tells us something about the past, the future, and the total amount of energy and matter in the universe. There are three broad categories when we talk about the shape of the universe: flat, closed, and open. These terms don't describe appearances, they describe geometry, how space behaves over vast distances, and to understand them, it helps to think in terms of lines and angles. In flat space, the rules of classical geometry apply. Parallel lines stay parallel. The angles of a triangle add up to 180 degrees. A circle's circumference is exactly 2π times its radius. This is the kind of space most people imagine intuitively, the kind that feels normal. In closed space, like the surface of a sphere, those rules bend. Parallel lines eventually converge. Triangles have angle sums greater than 180 degrees. If you move in a straight line long enough, you return to where you started. Space is finite in volume, but has no edges. It wraps around itself. In open space, the opposite happens. Lines that start parallel diverge. Triangles have angles that add up to less than 180 degrees. Space expands forever and curves outward, like the surface of a saddle, but extended into 3 dimensions. Which one of these applies to our universe depends on the total amount of energy and matter it contains. That includes not just visible matter, but dark matter, dark energy, radiation, everything. Einstein's theory of general relativity links that energy density directly to curvature. Too much energy, and the universe curves inward. Too little, and it curves outward. Just the right amount, and it's flat. This isn't just a philosophical distinction. The shape of space influences how light travels, how structures form, and how the universe will evolve over time. To measure curvature, scientists look at the oldest light we can see, the cosmic microwave background. Specifically, they examine the size of the temperature fluctuations, or spots, in that light. If the universe were closed, those spots would appear larger because the light paths would curve inward. If the universe were open, they'd appear smaller. But what we see matches the predictions of a flat universe almost exactly. In other words, space appears flat, not just locally but across the entire observable universe. That means the total energy density is very close to the critical value required for flatness. Not too much, not too little. This raises a follow-up question. How precise is very close? Could it still be slightly curved in a way we just can't detect? The answer is yes, it could. Our measurements have limits. The universe could be slightly closed or slightly open, just beyond our current ability to measure. But if that curvature exists, it's extremely small. On observable scales, the geometry of space is effectively flat, and that has implications. In a flat universe, space can be either finite or infinite, depending on its topology. If it wraps around in a way we can't yet detect, it might be finite but unbounded, like a 3-dimensional torus. If it doesn't wrap, and if it continues uniformly, it could be infinite. In a closed universe, space must be finite. It has a total volume. There's only so much room, though there's still no edge. And eventually, if gravity dominates, a closed universe could stop expanding and begin to collapse, leading to a big crunch. In an open universe, space expands forever. It's infinite in size, and the expansion never slows down enough to reverse. Distances continue to grow, and the geometry remains curved outward. The discovery of dark energy complicates this picture slightly. It's not just matter and radiation that influence the shape and fate of the universe. The presence of dark energy, a kind of pressure that drives acceleration, affects expansion regardless of curvature. That means a flat universe with enough dark energy can still expand forever. So shape and destiny are related but not identical. Even so, the shape tells us a lot. It tells us whether the early universe was finely tuned. It tells us how inflation worked. It tells us whether the cosmos wraps around or continues without repetition. And it gives us a sense of the overall architecture, not just what we see, but how it all fits together. There have been searches for signs that space might wrap, for repeated patterns in the cosmic background, or circles that match in opposite parts of the sky, as if we were seeing the same regions from different angles. But so far, no such evidence has appeared. If space does loop, the scale must be much larger than our observable sphere. This means we're left with a model that's flat, vast, and expanding. A universe with no detectable curvature and no obvious boundary. Whether that means it's infinite or simply large enough to seem that way is still open. But the evidence so far supports the flat model, not as an assumption but as a measurement, and that flatness is deeply connected to the theory of inflation. Inflation not only explains why the universe is homogeneous and structured the way it is, it also explains why space is flat. Rapid expansion would have smoothed out any initial curvature. No matter how the early universe began, inflation would have made space appear flat over large scales. And that's exactly what we observe. From here, we'll turn to another consequence of large-scale geometry, the role of dark energy, not just in shaping the expansion, but in defining the long-term future. Because if space is flat, and expansion is accelerating, then the horizon of what we can see will shrink over time. Light from distant galaxies will stop arriving. The universe will continue, but our access to it will fade. But for now, the shape of space remains one of the clearest indicators of cosmic history. It's not a matter of belief or imagination. It's a measured feature of the universe we live in, a clue to the structure beneath everything we see. For most of the 20th century, cosmologists expected the expansion of the universe to slow down. It made sense. After the Big Bang, space expanded rapidly, but gravity was always pulling things back. Every galaxy, every cluster, every trace of matter exerted a gravitational force on everything else. That force doesn't stop. So the assumption was, even if the universe kept expanding, it would do so more and more slowly over time. But that expectation turned out to be wrong. In the late 1990s, two independent teams were studying distant supernovae, explosions in remote galaxies that serve as standard candles. Because we know how bright these explosions should be, we can use them to estimate distances. And because the light stretches as the universe expands, we can also use them to measure how fast space has been growing over time. The results surprised everyone. The supernovae weren't as bright as expected. They were farther away than predicted by a slowing universe. That meant the expansion hadn't been decelerating, it had been speeding up. Something was pushing the universe apart, not just letting it expand, but accelerating that expansion. And whatever it wasn't accounted for by normal matter, or even dark matter. This new force, this unexpected component of the universe, was labelled dark energy. The name doesn't explain much. It's a placeholder, a way of describing something we don't yet understand, but the effects are measurable. Whatever dark energy is, it currently makes up about 68% of the total energy content of the universe. It's the dominant factor shaping large-scale behaviour. It acts differently from gravity. Gravity pulls, dark energy pushes. It doesn't clump, it doesn't form structures. It's smooth, evenly distributed across space, and as space expands there's more of it, not less. One model of dark energy treats it as a property of space itself, a kind of vacuum energy. In this view, empty space isn't really empty. It has a built-in energy density that doesn't go away as space expands. Instead, the total amount of dark energy increases with volume. The more space there is, the more of this energy exists, and the more it accelerates expansion. This concept ties back to Einstein's equations. In 1917, he added a term to his general theory of relativity called the cosmological constant. At the time, he believed the universe was static, and he needed a way to balance gravity to keep space from collapsing. Later, when the universe was shown to be expanding, he abandoned the constant, even calling it his greatest blunder. But now the idea is back. The cosmological constant, reinterpreted as dark energy, fits the data remarkably well. Still, no one knows exactly what dark energy is. It could be a constant, or it could be dynamic, changing over time, linked to a field we haven't discovered. That kind of model is sometimes called quintessence. It opens up possibilities. Maybe dark energy grows stronger, maybe it fades, maybe it's only a temporary phase. For now, the constant model fits observations. When we plot the distance and redshift of supernova, or examine the patterns in the cosmic microwave background, or study the distribution of galaxies, they all point to the same conclusion. The expansion of the universe is accelerating, quietly, gradually, relentlessly, and that has consequences. Not just for theory, but for what the universe looks like over time. As space expands faster, galaxies move away from each other more quickly. Eventually, their light will no longer reach us. Not because the galaxies are moving through space at impossible speeds, but because space itself is stretching faster than light can bridge the gap. The observable universe will shrink, not in size, but in content. Already, there are galaxies whose light will never reach us, no matter how long we wait. In the far future, even the galaxies we see today will fade beyond our horizon. The night sky will grow emptier. Cosmic background radiation will redshift into invisibility. The universe will still be there, but most of it will be beyond reach. This doesn't mean the universe is ending. It just means our access to it is fading. Light from distant places won't stop moving. It just won't get here. The expansion pulls everything apart, and the rate of that pulling is increasing. In the very distant future, trillions of years from now, only the nearest galaxies, those gravitationally bound to ours, will remain visible. Everything else will be too far, too dim, and too redshifted to detect. Civilizations that arise in that time may never know the true size or origin of the universe. To them, the cosmos will seem static and local. The clues we now have will be gone. This makes our current era unusual. We live in a time when we can still see the afterglow of the Big Bang, still detect light from distant galaxies, still map the large-scale structure of space. We're able to study dark energy while its effects are noticeable, but not overwhelming. That window won't stay open forever. The quiet acceleration isn't dramatic. It doesn't cause explosions. It doesn't bend space in chaotic ways. It just continues, steadily, subtly, shaping the universe 1% at a time. It's not something we feel, but it's there, embedded in every stretch of distance, woven into every photon travelling across the cosmos. We still don't know where it comes from. We don't know why its value is what it is, but we can measure what it does. And what it does is define the long-term behaviour of everything. From here, we'll move forward again into the questions raised by invisibility. If the universe keeps expanding and the horizon keeps shrinking, what happens to knowledge? What happens to the idea of observing something that can't ever be observed? Because in a universe governed by light and distance, the boundary of what we can see is also the boundary of what we can ever learn. In a universe where the speed of light defines what can and can't be known, visibility becomes more than just a matter of sight. It becomes a limit on knowledge, a horizon not only of observation, but of certainty. If something lies forever beyond our light cone, beyond any possible signal, beyond any future reach, can we still learn about it? Can we still say it exists? This isn't just a philosophical puzzle, it's a practical challenge in cosmology. Because so much of what we understand about the universe depends on indirect evidence, on interpreting what we can see and extending that interpretation beyond our observational limits. The question is whether that extension is reasonable. Right now, we can only see a limited portion of the universe, a sphere roughly 46 billion light-years in radius. That sphere is defined not by distance alone, but by time. It marks the region from which light has had time to reach us since the beginning of the observable cosmos. Everything beyond that is, by definition, unobservable. But that boundary isn't static. It changes as time passes. New light arrives. Distant galaxies come into view, or would if space weren't expanding. The trouble is, the expansion is accelerating. Because of dark energy, the light from many regions will never reach us, even if we wait forever. That means some parts of the universe are not just currently hidden, they are permanently inaccessible. No telescope, no probe, no future civilization will ever make contact with them, and that creates a hard line. If no signal can ever reach us from those regions, then we can't directly test any claims about them. We can't confirm what they're like. We can't know whether they contain galaxies, stars, or anything at all. We can only guess, based on what we see nearby, and based on how we believe the universe behaves on large scales. This is where inference comes in. We assume, for good reason, that the universe is roughly the same everywhere, that the same physical laws apply, that the same processes occurred in other regions as they did here. This assumption, the cosmological principle, is built into most models of the universe. It's supported by the uniformity of the cosmic microwave background, by the distribution of galaxies, by the success of large-scale simulations. Still, it's choice, a framework, and it means we often treat unobservable parts of the universe as if they're extensions of the observable part. If the universe looks the same in every direction we can see, we assume it continues that way beyond our view. But assumptions have limits. We can test them within our horizon. We can't test them beyond it. And that's where the boundary between science and speculation becomes sharper. Take the multiverse, for example. Some models suggest that entirely different regions of space, beyond our horizon, may follow different rules, different constants, different histories. These regions are forever disconnected. Yet they're part of theories that also explain things we can observe. So the question arises again. If a model predicts something that's unobservable, but also explains something that is observable, is the unobservable part legitimate science? Or is it just a mathematical byproduct? Different scientists answer that differently. Some argue that predictive power, even if limited to the observable region, is enough. Others argue that science requires testability in principle, not just practical success. If something can't be verified or falsified, even in theory, then it lies outside the domain of empirical knowledge. But there's another way to think about it. Science has always extended itself beyond direct observation. We don't see atoms, but we accept them because their effects are measurable. We don't see gravity waves as ripples in space, but we detect them through motion. We didn't see black holes for decades, but their influence on surrounding matter gave them away. In each case, the unseen became known through inference, through consistent, repeatable consequences. And even though unobservable regions of the universe are more distant than any of those examples, the principle remains. If a model explains the data, and that model predicts certain unobservable features, then those features carry some scientific weight. Still, there are limits to inference. There's a point where no amount of indirect reasoning can substitute for evidence. And in a universe where the observable horizon is shrinking, where dark energy is pulling regions away from view faster than light can travel, the opportunities for future observation are narrowing. That means the present era is uniquely rich. We can still test models against wide regions of space. We can still see the cosmic background, distant galaxies, and the large-scale structure of the universe. But that window is temporary. In the far future, many of these clues will disappear. So what does that mean for knowledge? It means that some questions may have permanently limited answers, not because they're impossible to ask, but because the information they require can't be gathered. That doesn't make the questions meaningless, it just means the answers, if we have them, will always rest on assumptions, even well-supported ones. It also means that the edge of our understanding isn't defined by curiosity or intelligence, but by the physics of space and time, by the simple fact that information can't travel faster than light, and that space itself is growing faster than that in some directions. But there's also another side to this. The fact that we can know as much as we do, about things billions of light years away, from events that happened nearly 14 billion years ago, is remarkable. That we've used light, theory, and measurement to map a universe this large is an achievement in itself. So while the unobservable universe may stay unobservable, we can still describe what's likely. We can build models with predictive power. We can recognize the limits of our tools without discarding the tools themselves. From here, we'll begin to turn toward time again, toward the future of this shrinking horizon and the role of observation itself. What happens to light in an endlessly expanding universe? What happens to the visibility of structure? And how does the boundary between what exists and what can be seen continue to evolve? Because even if some parts of the universe are unreachable, others are drifting toward that same boundary. What we see now may not always be visible, and what we know today may one day become impossible to confirm again. If we live in a universe where dark energy drives space to expand faster and faster, then the limits of observation are not fixed, they evolve. Over time, the boundary between what's visible and what's unreachable shifts, not because light stops moving, but because the space it has to cross stretches faster than light can cover the distance. This means the observable universe is not just a snapshot of the past, it's also a function of the present, and it changes. The horizon today, the farthest distance from which light has had time to reach us, is about 46 billion light years. But that number doesn't mean we can see everything within that sphere forever. Some of the light that's on its way to us now will never arrive. Some galaxies we can see today are already moving away so quickly due to the expansion of space that future light they emit will never reach us. This creates a kind of observational cutoff, not in the present but in the future, as the universe continues to expand, and as acceleration continues, more and more of the universe will slip beyond reach. That includes galaxies we've already seen. It includes structures we've already mapped. Their light will become increasingly redshifted, stretched into longer and longer wavelengths until it fades beyond the limits of detection. The process is gradual but irreversible. Over time, the night sky will grow emptier, not because galaxies are disappearing, but because their light will no longer be able to catch up. Even the cosmic microwave background, which currently fills all of space with a low faint glow, will redshift into wavelengths longer than any instrument can detect. Eventually it will fade completely. This future doesn't erase the past. The galaxies will still exist. The background will still be there, but they will no longer be visible. The observable universe will continue to shrink in content, even as it grows in size. We'll see fewer and fewer things, and the light that does reach us will carry less and less information about the universe as a whole. In the far future, long after the Earth is gone and the Milky Way has merged with its neighbours, observers living in gravitationally bound structures, perhaps in the remnants of galaxies, may see only a local group of stars. No external galaxies, no cosmic background, no sign of expansion. For them, the universe will appear static, cold and isolated. The clues that pointed to a beginning, an inflationary past, and a hot dense early state will no longer be accessible. The evidence will be gone, not erased, but unreachable. Cosmology, as we know it, will no longer be possible. That realization gives our present moment an unusual status. We live in a time when the universe is still readable, when the light from the early cosmos still reaches us, when large-scale structure is still visible. It won't always be that way. The timeline of the universe includes an observational horizon, not just spatial, but temporal. Some knowledge can only be gathered now, in this era. This horizon isn't just a problem for astronomy. It touches the foundations of physics. If laws are inferred from the way the universe behaves, and if large portions of that behaviour become unobservable, then what we know will become harder to test. Future scientists may rediscover physics using only local data, but without evidence of cosmic expansion, or relic radiation, or structure at large scales, their models may be limited in scope. And this isn't just a theoretical concern. We already know there are regions of the universe that are beyond communication. We already know there are structures whose future light will never reach us. The process is already underway. We're inside it. There are efforts underway now to record and preserve as much observational data as possible. High-resolution maps of the microwave background, catalogues of galaxy positions, measurements of redshift, simulations of cosmic evolution. These are the tools we use to extend our understanding beyond the local and into the global. But over time, the global view will fade. That doesn't mean science ends, it just means it adapts. Observers in the future will work with what's available. They'll build models that describe the universe they see, even if that universe is only a small patch of the original. And those models will still be useful, just more limited. The scale of a knowledge will adjust to the scale of visibility. There may be no way to reverse this, no way to communicate with distant galaxies once their light can no longer reach us, no way to re-extend the horizon. But what we know now, what we are learning today, can last. The information we gather, the models we build, the maps we draw, all of it becomes part of a record that can be preserved even if the sky itself grows dark. It's a reminder that observation is time-sensitive, that seeing the universe isn't guaranteed. It depends on where you are and when. And that our ability to study the cosmos at this scale is part of a narrow window in the history of space and time. From here we'll step into the final section. Not a conclusion, but a moment of pause, a reflection on the unknown itself. If light defines what we can see, and expansion defines what we can't, then what does it mean to live in a universe that is mostly invisible, mostly unreachable and still expanding? Because in the end, our understanding doesn't stop at what we can observe. It stretches carefully beyond it, into silence, into distance, and into the space that remains unknown. Most of the universe is already beyond reach, not because it doesn't exist, but because light from those regions will never reach us. The expansion of space is carrying them away faster than information can cross the distance. They're still there. Entire galaxies, structures, perhaps even other phenomena we'll never know. But for us, they are past the line. That line isn't marked by any physical boundary. There's no border, no signal, no sudden change. Just a slow shift. Light that never quite arrives. And over time, that unseen region grows as more of the universe slips beyond it. We still measure, we still observe, we still map the sky and analyze what's left within view. But that view is shrinking, not in size but in relevance to the total. The universe we can observe is becoming a smaller and smaller fraction of what exists, and we may never know what most of it contains. That fact doesn't stop discovery. It doesn't halt the work of science, but it shapes the edges of it. We build theories not just from what we see, but from what we can expect, based on the patterns so far. The universe appears regular, predictable, structured in ways that repeat across time and space, so we extend our understanding outward, across the invisible. Whether that extension is correct is something we may never confirm, but the process continues. Measurement, inference, modelling. The parts we can't reach still leave fingerprints on the parts we can. The early universe leaves traces in the background radiation. The shape of space leaves its mark on the distribution of galaxies. The force of dark energy reveals itself in redshifted light. But beyond that, beyond the last signals, the last photons, the last wavefronts ever to arrive, there is silence. Not empty, but quiet. Not gone, but unrevealed. There may be other universes, other versions of this one, other forms of physics, or regions where time plays out in different ways. If they exist, they are out of reach, not just practically, but fundamentally. Space doesn't just separate, it prevents contact. And so, whatever else may be out there, whatever else may have formed, expanded, evolved, it lies in the realm of what can be imagined but not confirmed. Still we sit here in one small region of space, at one point in time, with access to light that has travelled across billions of years, and we learn. We trace the patterns, we study the background. We measure tiny fluctuations and use them to infer the behaviour of matter before stars formed. We examine the present to understand the past, and we recognise that the future will limit that view more and more. There's no urgency in that, no drama. The universe will not end with a sound or a flash. It will simply grow more quiet, more distant, more difficult to read. And yet, the questions remain, not because they will all be answered, but because they are part of how we live in this space, this small patch of sky, surrounded by light that will never finish arriving. We ask not just what we can see, but what lies beyond. Not just what is true, but what is knowable, and where the boundary sits between the two. The answers, for now, come slowly, through data, through models, through inference, through silence. And somewhere beyond that silence, the rest of the universe continues, unobserved, unchanging from our point of view, unreachable and still real. Until next time, rest easy knowing that even in the silence beyond our sight, there's a universe still unfolding. Good night.